Hi, everyone. How's it going? Thanks a lot for joining us today. Wanted to welcome you all to Distilled Data Points. It's an online conference. We're co-hosting this with Dataiku, AWS, and Grid Dynamics. We'll be focused a lot today on doing data science more efficiently. We have three great speakers from Dataiku, AWS, and Grid Dynamics. Without further ado, I'd like to sort of give the mic off to our first speaker, John Posada from Dataiku. He's the partner solution architect at Dataiku. John, get us started.
Will do. Hi, everybody. How you doing today? My name is John Posada, and I am a partner solutions architect here at Dataiku. So to start off, what I would like to start talking about is operationalizing AI and what that means here at Dataiku. So for Dataiku, we've been around since 2013. We have a wide user base of over 300 plus customers. We have 20,000 plus users and 80% of customers expanding usage after their first year of using DSS, which we call Data Science Studios. We have a powerful industry leaders within inside the financial services. As you see here, we have Santander, BNP Paribas. We also have customers from consumer goods as Unilever, Sephora, as well as media like, for instance, 21st Century Fox and Ubisoft. We're also powered by a very strong organization of 407 Dataikers, and we have a global presence around the world. We have offices in Paris, London, New York, as well as Sydney, Australia. As of now, though, we are all working from our remote offices due to COVID-19. Now, we are backed by major partners as Battery Ventures, Iconic, First Mark, and also G Capital. So when I say operationalizing AI, what I really mean is there's three key drivers. The first one is inclusive. The transformation of AI must include all profiles. And that means collaboration across your organization is critical and enables upskilling initiatives. People, or as we also call coders and clickers, which is a term that we use here at Dataiku, will allow to work faster and smarter together. The second driver is then responsible. The transformation of AI must withstand a long-term objective of change of the organization. Responsible AI considers accountability, governability, and sustainability. And we're going to discuss that further later on in the presentation. The third driver then is productionalize. The transformation of AI must allow the benefits of AI to be pervasive across the organization. And that means going from self-service analytics to full-scale operationalization. So let's look at assessing your maturity level. There's usually two dimensions of data maturity. The first one is inclusive data science, as you see here, which means no data silos, no team silos, everyone's collaborative, and you have full employee engagement. And then the second dimension is operationalized AI, which is basically going from short time to operationalization as soon as possible. And the way that really usually starts at is big data zero. So basically, machine learning is for specialists. It's usually for ad hoc analytics, and then you usually have a siloed approach of team members or individuals. And then from there, you're going to go into, okay, how can we initialize that data and demonstrate some form of value? And then along that path, we go into like, what's the impact? What's the deliverable for the business value in operations? How can we then accelerate this impact by structure, execution, self-service? And then how can we go to systemization where we have fully aligned data, organization, and processes, and then finally end up at what we call enterprise AI. So what does data influence in an organization? As you can see here, we usually have four different personas, and these individual personas are the ones that really influence data in the organization. The first one can be between data scientists, engineers. That usually makes up between 0.5% to a 4% of data influencers, and usually data scientists are the ones that are building and integrating the very first building blocks for AI in the enterprise. And then from there, you have advanced analytics, advanced analysts. And those are the individuals that are performing cutting edge analytics on the data, tackling non-standard data and brand new needs from the business. And that's usually about 2 to 5%. And then from there, we go to analysts who are performing the regular analytics tasks that need to be augmented by AI with strong control and understanding. And they take about 10 to 15% of influencers. And then finally, the last 80 to 85% influencers is basically everyone else. You do not interact directly with AI, but they do benefit from AI as it's directly integrated into the business systems. So what does this mean? Well, before I can get there, first thing we have to look at is from different articles and different organizations like the New York Times, AI could worsen the health disparities. What that means is in a health system riddled with inequality, we risk making dangerous, biased, automated, and invisible decisions. That means we have to be very careful with AI and what AI can actually do for us in the industry. Here's another article, and this is from MIT Technology Review. AI is sending people to jail and getting it wrong. Because we have such strong bias that sometimes we might not consider in our data and also in our models, we can make mistakes from the past that we shouldn't really be making. That can make AI very dangerous because we're not holding AI to its responsibility. Here's another article from Berkeley News, which talks about mortgage algorithms for perpetuating racial bias in lending based on specific studies that they've actually done. So what this all means is responsible AI is the idea of developing machine learning systems that are accountable, sustainable, and governable. That is, that they do what they're supposed to. They remain reliable over time and are well-controlled and auditable. So some of the critical components of responsible AI. The first one is governance. As I mentioned beforehand earlier on, when it comes to governance, a view of which teams are using what data, how, and which models is a must-have. That also means that we need to trust that the data is reliable and being collected in accordance with regulations, that we have a centralized understanding of which models are used for what business processes, and that we don't have any shadow IT. That then leads us to the second component, which is sustainability. We must have infrastructure that's built for the future, and that means leveraging the best technologies in a controlled way, whether that means you're in the cloud, you're in a hybrid environment, or you're on-prem. And then from there, we're going to go to reliable continued access to data used to support current or future data projects. And lastly, it's a centralized place to really monitor models in production with people that are accountable to their maintenance. The third component then is accountability. And a must-have for that is assurance that data is used for AI projects that comes from compliant and unbiased sources. And I'll repeat, that's extremely important. So please keep that in mind, especially when it comes to responsible AI. And then having a collaborative approach to AI projects that ensures multiple checks and balances on potential model biases. We usually call this a human-centered approach. And that means providing people with the tools plus trainings to be aware of and then execute on all three components. So what this leads to is that Dataiku as a unified platform brings together people, processes, and technologies. It's really a comprehensive and collaborative data science platform that enables teams of analysts, data scientists, engineers, and also managers to effectively collaborate with each other, work with evolving technologies, and drive the AI projects from the design phase into production. As you can see here, what we usually like to call that is end-to-end solution, using open source technologies, have a collaborative platform between different personas, and be focused on production. What I mean by that is taking a process, a workflow that's been designed in the design phase into a production environment that can be used almost immediately. Now let's talk seriously about powerful data and analytics. When it comes to enterprise AI, there is a fundamental challenge, and that's not usually software. It usually starts off with siloed data. That means that data is most often there and in many different forms and many different systems that need to be combined. That means you have different data sources, and not everybody might have access to those data sources, but they do need access to it to actually determine how to move forward with a project or a workflow or a process. The second challenge is siloed people. Success is not usually defined by having great business acumen or fantastic data skills or even great analytical mindsets. You need all of them to work together in a collaborative platform. And lastly, you have siloed processes. Whether you're looking at a team that focuses on the labs, or you're looking at IT, whether you're looking at data, whether you're working with operation teams, or even different business teams, they all have their own processes, and value delivery requires to bridge them all together into one potential solution. So if we consider solution overview, then we have an end-to-end solution from data access to operationalized models. So what does that mean? Well, with respect to Dataiku and DSS, the platform that we call Data Science Studio, as you can see here, we have three different sections. The first one is how to manage your data. The second one is machine learning, and the third one is model deployment. And each window and screenshot that you see here really represents a specific environment inside of DSS. So the reason this is important is because when you have different personas that are working together in this platform, say for instance, a business analyst, the first time a business analyst can find and understand and prepare data by looking at what we call the visual auto prep. That basically means the data source gets imported into DSS, and now you have the option to like visualize that data, analyze it, look at what type of discoveries you haven't noticed before. Is there any NaN values and things of that nature? And then from there, when it comes to the machine learning process, where you have what we call visual auto ML, and you're building visual pipelines and workflows, you need to figure out as a business analyst, how can we prototype some of these models and then integrate them so we can work together with other personas. And then lastly, with the model deployment for business analysts, they're going to be able to really monitor results, whether that means they're using a dashboard where they're going to deploy a model and see how often that model is actually receiving specific HTTP requests or pings, or how often is it actually available, or how often is it actually down. From this persona, we then go to the data scientist. Now, the data scientist, that individual and that persona is really building plugins, and plugins can be built with programming languages, like for instance, R, or maybe even Python in the back end with inside of DSS, or maybe they're actually building that themselves using what we call recipes, which are the tools that go inside of workflows. Different processes, basically different steps. As you can see here, that's something that they're going to communicate with the business analyst. At the same time, they can also help build business monitoring dashboards for business analysts so that analysts can then monitor the results from those dashboards that have been built. by the data scientists. But that doesn't just stop there for data scientists. Data scientists can also use for productivity and extend current visual processes that have already been set up when it comes to actually investigating the data that's being fed into DSS, as well as use as a baseline a way to optimize currently existent on the machine learning models that have been built for them and inferred based on the data that's available inside of DSS that you're providing as a user. And then from there, we go to the data engineer persona. This is the individual that's going to be responsible for how can I optimize pipelines? In other words, can I make them a lot faster? Can I figure out how to set up different processes? Can I figure out how to maximize specific programming languages by optimizing some of the code, maybe using different environments like Kubernetes, something like Spark, or maybe Spark inside of Kubernetes as well. And then how can they integrate these pipelines and these workflows into developing models so that can then be integrated in a real life business process or platform, for instance, using a mobile application or even a web application. And then from there, we're going to go to the last persona, which we like to call the analytics leader. This is the individual that's going to be responsible for understanding the visual pipelines that have already been created by the different personas of team members inside of a project for these workflows, as well as monitoring the results and making business impactful decisions in the business based on what they've seen on, for instance, a model that's been created and is providing value to the business at that moment. Now, what this means is there are two key modes of data innovation, really, and we like to call this enabling self-service analytics and operationalizing ML. So what that means is we have a little term that we came up with. It's called O116N, and that means building robust solutions to business challenges, and that can be either done at the organization-driven level, it can be focused on specific tasks or specific projects, it can be looking at longer-term results, how to integrate processes and steps, as well as high-value projects. And then we also have what we call SSA, that means self-service analytics, as you can see here below. And that is, how can we get quick answers to unformulated questions that have been directed by end users, and how to make agile and instantaneous decisions when necessary. As you can see here, operationalization and self-service analytics play a role together, but in different ways. In this case, we have a data team with different personas. As you see here, we have the business analyst, we have the data scientist, we have the analytics leader, and then the data engineer that can work with different teams like the risk team, operations, marketing, or even the executive management team. So what this really means is, how can we unleash the full potential of enterprise AI? So we came up with a new formula. We say O116N plus SSA equals the AI acceleration formula. That basically means how can we ensure depth and with operationalization of the processes with respect to your platform and your workflows, as well as how can we secure coverage with self-service analytics. That means how can we package tools for maximizing the reuse of those tools? How can we centralize emerging key data, as well as how can we automate repeatable processes and then build on the major global successes of all of these processes and models that are being built as well. And then how can we build on the many local successes of different team members, different groups? Like that means building a pervasive data culture, quick execution of small projects, and freeing advanced resources for larger ones. As you can see here, the circle goes round and round. So how can we future-proof your data effort? How can we get results today and build for you for tomorrow? Well, there's different ways to look at that. The first one is we like to leverage existing skills and secure sustained availability. That means if you have data engineers or data scientists that like to work with, for instance, Python, Scala, R, SQL, Shiny, or Cloudera, we leverage those tools and we leverage those platforms and say, just bring that into DSS. There's no restriction there. We also like to maximize usage of most up-to-date technologies. That means if you're doing a lot of heavy deep learning processes and you want to use TensorFlow, or you want to use scikit-learn for most of your machine learning models, Keras, or even bring in Jupyter Notebook for your editing of your Python models or your R models or even Scala models, we enable that. And we want to make sure you maximize that within inside the platform. We also like to use current infrastructure and be ready for tomorrow because, at the end of the day, the industry is constantly growing. That means that you can have cloud providers like GCP, Microsoft Azure, AWS that are constantly growing and providing new features and new services. Well, guess what? We want to take advantage of those features and those services and enable you to continue to use them inside of the DSS platform. Because at the end of the day, we are agnostic with respect to different technologies and different platforms. That means also taking advantage of Docker, or maybe using NVIDIA because you want to take advantage of the GPU processing units that they do offer, as well as different databases like Teradata or data warehouses like Snowflake. And then what that also means is we like to extend based on current and future operating requirements. If you already have organizations that we seem to have to use Tableau on a daily basis or Qlik or Alation or Esri, that means that we're not going to tell you, hey, don't use those platforms, or we're not going to restrict you. As a matter of fact, we're going to enable you and say, hey, once you've built these workflows and these processes, well, whatever data is exported, you can go ahead and feed that into these other processes that you're already currently using in your environments, in your industries, and in your different departments and groups. Now, with that being said, before we move on to Benoit, one thing I do want to show you is that we do have an article and stories that you can read about how machine learning helps different organizations. In this example, we have Levi's, who's been able to enhance their e-conference experience. And the way they were able to do that is they're using Dataiku DSS and Amazon Web Services to really create a recommendation system that aligns to a customer's journey, such as showing the best-selling products in the region to new customers or displaying complementary items to complete an outfit to return purchasing customers. That goes to show you the power behind the platform, and as well that the platform can work collaboratively with other partners and other groups and other processes and other steps as well. So thank you for listening to this part of the actual webinar demo. Now the next step I would like to do is push it off to Benoit from AWS. Benoit?
Hi, John. Yes, thank you. That was a great introduction to Dataiku platform. So as John mentioned, the Dataiku platform, I love this platform personally. I'm a partner solution architect in AWS, and I work with many AWS partner companies, and Dataiku being one of our leading partners in the data science and machine learning platform space, right? So the reason I love the product is not only just the visual interface and the ease of use that it provides to many different stakeholders, starting from business analysts to data scientists to operational engineers, but on top of that, it does provide the flexibility, as John was mentioning towards the end of his portion, that it allows you to democratize new technologies and at the same time allows you to leverage your existing infrastructure investment. With Dataiku and AWS, it allows you to use your existing infrastructure. So let's say you have your workload running on AWS, or you have your data staged on a AWS-based data lake using S3. So with Dataiku, you can very easily integrate with all the different data sources that you have on AWS. On the other hand, if you have compute needs, right? So today, you can compute on your Dataiku DSS instance itself, but if you have needs to scale out your compute, with Dataiku, you can easily use EC2 or EMR or EKS or AWS SageMaker to scale out the compute need. And I'm going to go through all of these in details in a moment. So this one here is a representation of the many different components of AWS that you can use in the different stages of your data science project, starting from connecting to the data store, to exploring and preparing your data, to finally train and deploy your model. So when it comes to connecting to data source, so you can use Dataiku recipes to connect to any API-driven services on AWS. And on top of that, you can also connect to S3. You can query data directly from your S3 bucket using Athena. You can use Glue metadata store and for ETL jobs. When it comes to exploring your data in AWS services, you have option to prepare recipes that allows you to explore data either in S3 or in Redshift, and you can do in-database processing of data to prepare the data set that you can then use on a Dataiku decision flow. When it comes to training, you can use, as I said, you can use EMR, which is our managed service for your Hive and Spark processing, or you can also use Elastic Kubernetes cluster on our EKS service. So in this diagram, it just shows reference architecture where it is showing that you can use your DSS design node, which is the server that runs your Dataiku DSS application running on your public subnet. And at the same time, it can connect to any of the services that is running either in your private subnets, such as Amazon Redshift, EMR, or EKS. And at the same time, other managed services that may or may not be running inside your VPC using VPC endpoints or the public endpoints, such as you can use identity and access management to control access to your data sources. You can use S3 and Glue and Athena to query the structured and unstructured data. And you can use Amazon SageMaker to train and deploy your model using the SageMaker algorithms. And on top of that, Dataiku also have tight integration with our high-level AI services, such as Amazon Recognition and Amazon Comprehend, that allows you to do AI tasks without even training your model. And all of these you can use within a single flow as your use case might dictate. So quickly going into some of these integration points with S3 integration, You can connect to object storage in S3. You can do Cloud SQL on Redshift, Athena, and RDS, and then use Glue metadata store to store the metadata of the data that you are storing on your S3-based data lake. When it comes to offloading computation, the choices there are, as I mentioned earlier, you can use in-database processing in Redshift or RDS. You can also use SageMaker for machine learning model training, and you can use Hive or Spark using either EKS cluster or EMR. For in-database SQL processing, it does support reading your input tables. You can perform the SQL queries, writing output tables, and you can push all of this computation directly into the database, thereby freeing up your compute need in your DSS node itself. Similarly, you can query your data on Redshift and push the computation to Redshift as well. And that allows you to condense consecutive SQL recipes into a single step with your SQL pipelines. With Athena, as many of you might know, it allows you to run SQL-like queries on the data that you have stored on S3 as objects. You can also use Glue Metastore when you run on AWS using managed services like EMR or EKS or Athena. You can connect to DSS to an EMR cluster to submit your Hive or Spark jobs, and you can also use Amazon Machine Image that Dataiku offers on AWS Marketplace to create EMR cluster with the Dataiku application in itself. Lastly, on Spark and Kubernetes, you can either create a new Kubernetes cluster or connect to an existing cluster. And if you have needs to run Spark, PySpark, or Scala jobs, you can directly submit those for computation on EKS cluster. And then finally, for SageMaker, you can use SageMaker to prepare data, utilize the visual interactive Python notebooks that runs on SageMaker, and utilize the models in SageMaker, trained or deployed, right? So when I say trained or deployed, I mean you can have your model trained on Dataiku and have it deployed on SageMaker, because SageMaker provides a very robust model deployment platform that allows you to scale your model as the traffic grows. On the other hand, you can also use SageMaker or the SageMaker built-in algorithms. So currently, we do offer 16 different machine learning algorithms as native algorithms within SageMaker. So you can also submit your job to SageMaker and use one of the SageMaker algorithms to train your model and have it deployed there. And lastly, this is just an example of what our AWS Power Flow might look like. Whereas you can see the tables are read from Athena, and then you can use like visual recipes to do some in-database SQL processing. Following that, in the exploration phase, you can distribute visual machine learning using EKS, and then read and write to S3 using your Glue Metastore, using the metadata that you derived and stored in Glue. And then finally, you can use EMR to process the data within the cluster and then write any outputs that you might want into a Redshift database. Now, this is just a sample here. When in the later stage, when Elia will show you how they created this application, you will see an actual example of how they have used in Grid Dynamics, how they have used another process flow from Dataiku that uses some of these AWS components there. And that's all from my side. I am happy to take any question and answer them on the chat window. So John, you can take it over from here.
Great. Thank you so much, Benoit. I appreciate that. Well, as I mentioned beforehand, if you'd like to explore Dataiku DSS for yourself, then just please download the free trial. This is the link that we have available. You can just go there and download DSS Lite as well, or really any of the other tiers that we have and test it out, and then come back and give us some feedback. Or if you have any questions, just please follow up with us by email. But beyond that, I would like to move it forward to Ilya from Grid Dynamics. Thank you, everybody. Ilya?
Thanks, John. Thanks, Benoy, for your presentations. So let me start. My name is Oleg Katsov. I'm a head of data science practice at 3Dynamics. And in this talk, I'm going to show how some applicable use cases like personalization and customer analytics can be solved on top of data IQ, and also talk about some emerging techniques that can help to simplify model design, that can help to simplify data engineering for this type of modeling. First, let me briefly introduce 3Dynamics. We are a data science and engineering services company that works with leading retail, manufacturing, finance, media, technology companies, and we focus on helping them to embrace emerging technologies and use data science, use machine learning, use operations research to optimize their marketing operations, supply chain management, revenue management, and other areas of enterprise operations. And we are recognized as leaders in this space because of this strategy focused on innovations and focused on emerging technology. So in this talk, I'm going to talk about some lessons that we learned through implementing customer intelligence solutions for Fortune 500 customers in last couple of years across different domains. And I'm going to talk about what are the limitations of traditional personalization methods and what kind of problems we encountered during implementing the solutions, and how we worked around these problems using some novel, some emerging machine learning techniques. And after this introduction, after this overview, I'm going to show a live demo of how one of these techniques can be implemented actually on top of AWS and DataIQ. So let me start with some very brief, very basic overview of traditional personalization techniques, just to set the stage. So one of the most basic techniques that people are using all across the industries, especially in advertising and offer targeting, is lookalike modeling. This is very basic technique, and the idea is that, let's say that we have some historical customer profiles, we can take demographic information, we can take behavioral information, interaction with merchandise, click streams, and so on, and create customer profiles building essentially a vector of aggregated features that describe a given customer. And then we can describe some metric of interest. It can be conversion, it can be churn, it can be something else, depending on what is our objective. Are we trying to acquire customers or retain customers? And then we train essentially a classification model that is able to consume some customer profile as an input and score this customer, how likely this customer will convert or how likely this customer will be churned, depending on who this customer is similar to among our historical examples. And then we can make a decision with regard, should we provide this customer with an offer and what kind of offer it should be. And of course, this schema can be extended with some additional elements like lifetime value estimation, so we can make monetary decisions and so on. Another very popular technique, especially for recommendations, is collaborative filtering. I assume most of you are familiar with it as well. So typically in collaborative filtering, the problem is framed as we have user item interaction metrics, and we have some recordings of how users interacted with merchandise through clicking on them or through purchasing some items. And then we frame the problem as metrics completion. We essentially trying to predict purchases or trying to predict ratings in missed elements of these metrics. And of course, this problem can be mapped to lookalike modeling, to a similar technique as it is shown here, right? We can take this user item interaction metrics and convert it into the sparse vectors, and this way we can see that essentially these two problems and these two problem formulations and these two techniques are dual to each other, and we can actually convert collaborative filtering problem into lookalike modeling problem and vice versa. And this way, these techniques, they actually share many of the drawbacks and advantages. Now, it is important to understand that these techniques, these basic techniques, they work really well in some settings, and ideal settings is that we have some very well structured storage of customer behavioral information, of customer demographic information, ideally a relational database. And then we take this input information to build our features, and then we train the model, and it works. But at the same time, in reality, in many real settings, this process is not that simple, and there are a lot of complications, a lot of hurdles in addition to that. For example, in many environments, we actually need to engineer features based on application logs or based on mobile application logs, server logs that contain multiple clickstream events, multiple interactions with customers. And of course, interactions with customers, they're sequential in nature. We typically have multiple touch points and multiple purchases, multiple clicks, and so on. And this information about this temporal structure of interactions, it can be lost in our aggregation once we do lookalike modeling, once we do collaborative filtering, just because these methods are designed this way. And of course, we need to do a lot of feature engineering, and it can be quite complicated if we deal with non-structured or semi-structured sources of data, like application logs that typically not documented well, not maintained well, subject to frequent changes, and so on. The second problem is what is typically called cold start, is we do not necessarily have complete interaction information, behavioral information about customers, and we generally need to incorporate product descriptions, product images, maybe some graph information about transactions between the customers, and so on. And manual feature engineering is not very well suitable for doing this. And finally, the third group of problems is that strategically we need to optimize not just individual outcome like churn or conversion, but we would like to optimize the whole sequence of interactions in the future with the customer. And this way we do not necessarily need to do just myopic optimization, but we need to do a strategic optimization of this interaction sequences. And these problems are not really addressed by traditional techniques that I just mentioned. But fortunately, in recent years, we see like increasing adoption of emerging novel machine learning techniques all across the industry that help to work around these problems. First of all, to deal with this problem of sequential modeling of sequential inputs and complexity of feature engineering, we can replace manual feature engineering with more advanced models that can either consume sequences of interactions with customers or can learn features in an unsupervised way. And this will be the primary focus of our demo today. If we are talking about incorporating various types of data like images and textual descriptions, then this problem can be alleviated by using deep learning techniques and essentially replacing basic collaborative filtering techniques like metrics factorization with more generic neural networks that can incorporate embeddings produced out of images and out of texts more easily and model more complex interactions between all these different sources of information. And finally, to work around myopic type of optimization and optimize interactions with customers strategically, we can use elements of reinforcement learning and frame the problem as essentially Markov decision process, as a multi-step optimization, and try to optimize not just individual actions, but sequences of actions. But in this presentation, I'm going to focus on this first bucket around feature engineering specifically. So what can we do to work around this complexity of feature engineering and incorporation of sequential inputs? There are different ways how it can be done, and I will explain it in steps, and the steps can be actually mixed in different ways in actual applications. The most basic technique that we can try to use is to use some sort of sequential neural network, sequential input neural networks like LSTMs. And this way we can build a network that consumes not aggregated features, but features for individual events, as it's shown here, right? We essentially will represent each event as a vector of some features, of some numbers. What's the type of event? Is it a click? Is it a purchase? Is it something else? And other attributes. And we have a number of such events, a number of such vectors, and we have, of course, multiple journeys for different customers. And then we can essentially run our LSTM model on top of it and produce some forecast, and at the same time, the hidden state of LSTM network can be used as embedding of a customer, embedding of a customer journey, and we can do clustering or some other analysis on top of it. And this is actually very efficient in the situations once we need to predict customer behavior based on just a few events, few samples, which is particularly important, for example, for customer churn analysis. And we see that this technique is quite powerful in that regard. And of course, it also simplifies feature design because we do not need to invent how aggregated features, but we can just feed these individual events into the model. Our next step is actually to recognize that we do not necessarily need to use this type of generic neural networks, and we can use something more specialized. For example, we can take advantage of NLP models that originally were designed, of course, to process texts, to process sentences. But we can recognize that we can interpret customer interactions essentially as some sort of text, some sort of sentences. For example, if we have a number of historical orders, then we can represent each order as a sequence of product IDs. And in that case, each order will be essentially our sentence, and each product ID will be a word. And then we can use NLP techniques, for example, word2vec, to learn embeddings for these products, and then we can do analysis of our products in this semantic space. And this is a great technique. This is a great approach because it can be implemented very easily, and I will show how exactly it can be done in a moment in our demo. Then we can go even beyond that and try to incorporate, let's say, some content information into the mix to deal with, let's say, to alleviate to some extent cold start problem if we do not have a lot of detailed behavioral data, or we would like to take advantage of some product attribute information that we have in hand. So this way, for example, we can replace product IDs by actually sequence of product attributes. For example, we know that each product corresponds to a number of attributes, and that we can replace each ID with a sequence of attributes and create these attributes sentences, and again apply some model like word2vec or doc2vec to learn embeddings for individual product attributes this way. And then on top of it, we actually can do some algebra around these embeddings that we learn, and we can use these embeddings in many different ways. And it's important, of course, to understand how exactly it can be done and what are the use cases. For example, if let's say that we learn embeddings for product attributes, and it means that using these embeddings, we essentially can construct new products for, like embeddings for new products for which we do not have historical sales data. And by, for example, averaging or just summing attributes of this previously unobserved product. And this helps to alleviate the cold start problem, and then we can use it to do some analysis of this product, so to do some recommendations for products, for new products for which we do not have historical data. So once we have a product embeddings, or we learn product embeddings directly, then we can use it to compute similarities between the products and use it for recommendations, of course. We can aggregate product embeddings into session embeddings. For example, if we have a user session, like online session, then we can calculate the average of product embeddings that user interacted with during the session. And this way we can create an embedding that describe a session, and we can use it to do some in-session personalization, and this can be done quite easily in real time to do so. And finally, we can learn customer embeddings or aggregate these customer embeddings from product embeddings based on customer interaction history. And these embeddings, again, can be used either to do some downstream modeling. Essentially, we can take these embeddings and use them as input features to downstream models, for example, LTV models or recommendation models, or we can compute different types of similarities between customers to, let's say, identify customer segments, or to measure willingness to pay for different customer groups, or for new customers, learn their payment preferences, and so on and so forth. So this is very, in that regard, this is very flexible and very powerful. The next step, the next technique that we potentially can apply on top of it is to learn customer embeddings directly, not just assemble them from product embeddings. And one thing that we can do, we can represent each customer, each user as a number of sentences where each sentence corresponds to one order, and each order in turn is represented by a number of product IDs. And then we can apply doc2vec and learn customer embeddings, customer representations in this semantic space on top of it. Actually, it's not necessarily better than learning customer embeddings through aggregation of, let's say, product embeddings or attribute embeddings, but it actually depends on the use case. Typically, it makes sense to try several techniques and see which one works better. The next important step that we can do, we can try to learn actually embeddings directly from application logs. And this is of course, very, very important because it can help to simplify our feature engineering dramatically. So let's consider the following example. Let's say that we have some server log, and the server log includes a timestamp. It includes some event name. It can be like browsing of a certain page or a purchase or something. And then it can be complemented with some attributes like a product ID or specific type of action or some other attributes. So this is, as you can see, this is a fairly generic log structure. And then what we can do, we can just mechanically produce some tokens based on these attributes. For example, we can just concatenate event name with attribute name and with attribute value and associate each customer with a sequence of such tokens. And then again, we can apply some unsupervised learning techniques like Word2vec or Doc2vec to learn customer embeddings from this representation. And the beauty of this approach is that we do not even need to understand semantics of logs in many cases. We just mechanically transform logs into the sequences of tokens and do our learning on top of it without doing, essentially without doing any engineering at all. And then these embeddings can be used as inputs to downstream models, and it can help to achieve quite good results, actually comparable to the results that can be achieved through manual feature engineering. And finally, the last technique that I'm mentioning here is that we can combine these unsupervised learning methods that I just described with some supervised learning techniques. And the rationale for that is that for unsupervised learning methods, we do not have any guarantees what kind of embeddings we will learn, and these embeddings may or may not be aligned well with what we are trying to predict or what we are trying to optimize in downstream models. So it can be good to combine it with some supervised, with some target metrics to essentially realign this embedding space, the semantic space, with what we are interested in from, I don't know, recommendations or prediction standpoint. And the way it can be done, one of the techniques that can be used here is that we can, let's say that we have our Word2vec model, we can do some, this model, of course, it's trained in an iterative way. It's a neural network internally, and internally it contains an embedding matrix that essentially represents the number of weights for different input words for the context from which we are trying to predict the next word in the sentence. And then we can, let's say, do one training epoch on this network and take this embedding matrix and copy it into some supervised model, into some other network that is trained to predict some target metrics, do a training iteration on this network and copy these embeddings back to our Word2vec model, then repeat the process many times iteratively. And this way, on each iteration, we essentially like shifting, realigning our embeddings in unsupervised model with embeddings in the supervised model, which is focused on some set of target metrics. It can be one target metric, it can be multiple. That is an overview of the techniques that we can use, and hopefully it gives some idea of what are the benefits and what are the advantages of this type of methods. And next, I'm going to move forward to the actual technical demo and show how like a simple version of these techniques was implemented. And for this demo, we actually going to use very simple data set. It's like a real data set that includes some orders that are associated with user IDs. These are online orders, a sample of data from online grocery store. And each order is, of course, associated with line items with specific product IDs and the sequence numbers for these products, how they were added to the shopping cart online. And then each product has a name and has association with aisle and with a department. And there are some other fields, but we will not use them in this presentation. So what are we going to build in Dataiku and AWS is the following. We have, as I will show in a moment, we have all these different data elements, these different tables sitting in AWS S3 buckets. And then we will do some very basic preparation of this data. As I mentioned previously, we do not need too much data engineering in this case. So we will do just basic data preparation. Essentially, we will join all these data sets together using Dataiku capabilities, and we will create a simple dashboard that we will use to control the quality of this data and monitor some basic properties of this data. And this flow will be executed on top of AWS EMR. Essentially, it will be transformed into a Spark job. And then we will have two different implementations of our item-to-vec model. First, we will implement it using Jupyter notebooks. In this notebook, we essentially, like simulate what a data scientist will do to explore how the model can be implemented and play with this model around. And the output of this model will be our word-to-vec model and a set of embeddings that can be placed on S3 bucket. And we will again measure some properties of these outputs for quality check purposes. And then we will copy some parts, some production version of this code into a production job. And then it can be executed on a scheduled basis. And again, the quality can be measured and the outputs can be placed in some storage in AWS S3 in this example. And then we will develop a very simplistic recommendation system on top of this model. And in reality, it can be something more sophisticated, but the workflow will be pretty much the same. So let me now go to the actual DSS instance and show you how it was implemented. So we have all the steps already implemented in here. So I will just execute some of the steps, but not all of them for the sake of time. But actually the flow is relatively simple, relatively straightforward. So hopefully it's quite easy to understand all the steps. So as I said, we have all these data sets sitting here in S3 buckets. And then we can use this flow designer to create some data transformation flow using different recipes. We can use either some standard recipes like group by or joins or some other data preparation steps, or we can create our custom recipes, essentially Python scripts or Jupyter notebooks or Spark jobs here. And what we are doing here is very simple. We just join several data sets together to produce the data set that is prepared for training our model. And here we actually have EMR sitting behind this process. So I will not execute this job in real time because it takes a few minutes, but I can show you an example of an output of this process. For example, here you can see that once we execute a job, once we execute this flow, it is essentially converted into Spark application, and the Spark application is executed on top of EMR in automated way. So we do not actually need to deal with implementation complexities here. And then for this output data sets, we can explore them here, or we can even calculate some basic statistics. For example, here in this screen, we have a breakdown of how number of orders is distributed by different days of the week and by different hours within the day. So we can do this type of exploratory analysis in the beginning. And then here we will add, let's see, here we will add a simple script that computes some basic statistics of these different data sets, both original ones and pre-processed. And saves these statistics to some small table that we can use to control the quality of the data. And we created a dashboard here for input data that describes these basic statistics, like what's the number of rows in each data set, what's the memory footprint, how long does it take to load it in memory, and also some visualizations like the distribution of sales volumes by departments and so on. So this way we can, if the flow is executed in automated mode, we can watch this dashboard and see that our metrics are generally doing well, that we are not losing any data or something. And then our next step will be to create a notebook in here. So we created it already with different steps to learn our embeddings and to train our word-to-vec model. So here, the workflow is very straightforward. We of course have some imports, and we import some data IQ tools here, and I will show in a moment why we are using it. We are using it to load data sets just by dataset ID from what we produced in the flow. And then what we do here, we do one additional data transformation step. We essentially convert our orders into sequences of product IDs. So I will just go and execute this process here really fast. We have very powerful machine here with 36 cores. So we process around, I believe, more than 3 million orders in just a matter of a few seconds. Just give it a little bit more time. Yep. So it's 3 million, more than 3 million orders. And our output is, as I described before, is just a sequence of sequences of product IDs that we can use to train the model. And the model training is also very straightforward. So we have here some scaffoldings around login and so on, but essentially the idea here is to use standard word-to-vec implementation from GenSim. We just set some parameters, adjust some parameters, and then we feed this basic product corpus is input into the model, and then we train this model, and then we save it to our local file system. So let's give it a couple of seconds. This training process is also relatively fast. It will take just 10 seconds or something to produce this model. But meanwhile, I will briefly talk through the next steps. So in the next steps, meanwhile we are training this model, we are going to take a few product IDs, like very typical product IDs, like organic bananas, blueberry waffles, low-fat milk, and explore the semantic space around these basic products and see that we are getting some reasonable results. For example, that in this semantic space, bananas are similar to other fruits and things like that, to make sure that we are producing some reasonable results. So all right, so we have our model ready by that time, and it is saved to the local storage. And then let's do this reality check and show a few examples. So you can see here that if we take more similar vectors in the semantic space to our input products, then we are getting somewhat reasonable results. So indeed, bananas are surrounded by bananas in this space and other fruits, and these dessert products are like waffles are similar to oatmeals and ice cream and so on. This means that our semantic space, it captures some semantic dependencies between the products based on how people actually purchase them, how people essentially use them. And then our next step is to not just do these point checks, but to visualize the entire semantic space. We are going just to do the T/E projection of this space into a two-dimensional plane. And essentially what we are trying to calculate, we are trying to calculate a table like that. We have a product ID, we have product names, aisles, department joined with these product IDs, and for each product ID, we are trying to compute its two-dimensional coordinate in this semantic space. Okay, so again, it is done in a matter of seconds, and we can see here that this example, and we have more than 100 tiles and 21 departments here. And if we visualize this projection, then we can see that we are getting somewhat reasonable results. This results in the sense that our embeddings are aligned with our ground truth with departments. So for example, let's see, we have here, let's say, alcohol products form a cohesive cluster separated from everything else, as well as baby products, and also we have some reasonable results for other departments. But of course, there is no goal to learn this ground truth. We're just trying to learn, we're just trying to make sure that our embeddings, they reveal this customer behavior information, this customer behavioral patterns, and these patterns not necessarily perfectly aligned with department labels, but as we can expect, they are somehow somewhat aligned to a certain degree. And then we can save this output into the Data IQ project space. We can do the same thing for aisles as well, and compute similar visualization files as well. And then on top of it, if we go to dashboards, here we created here some output, a sample output dashboard that shows this this visualization of this embedding space and the tables with some basic reality checks that I've shown. And this way we can monitor that we are learning something meaningful if the project is executed on a regular basis. So as you can see, this is a very simple process, and we can do, actually we have another notebook for customer to work type of a model, and we are getting pretty much similar results there, but for customer clustering, customer analytics purposes, I will not show it for the sake of time, but conceptually it's very similar, and the results are also great in the sense that we are learning good and meaningful customer clusters in there. But in the meanwhile, we are going to proceed to our last step, which is a productization of our notebooks. What we are going to do here, we are creating a production version of this notebook, and in this production version we have again our model training with some data preparation, and we save our model into a folder here. So you can see here we have like 50 megabytes model of a 50 megabyte size here that we can use for production purposes. And then for production purposes, what we do here quite easily, we are going to our API designer here, and we have already pre-created recommendation service here, very simple one. I will just quickly show how it works. What it does, it essentially contains this simple Python script that just uploads our pre-trained model, and then it consumes some product ID as a parameter and returns nearest neighbors in this semantic space for this product. So this is a very simplistic more like this type of recommendations service. And then the service is deployed into another node here, and here we just go and deploy the script very straightforwardly here, and we have here, and we automatically get here an endpoint that consumes our product ID, our parameter, and returns this recommendation. So I can just take the sample invocation and go to this terminal and just execute it, and I'm getting this top 5 product recommendations for this given product ID. Of course, this is a very simplistic implementation, but hopefully demonstrates the idea very well, and we can develop, of course, something more sophisticated here. Okay, so that's it from the hands-on session perspective, and I'm ready to take questions.
Yeah, hey, Ilya. So essentially, we just launched a quick poll, and then you should have all received that right now. And also, if you have any questions for any of the speakers, feel free to just type them out in the question and answer section. We already have a couple of questions. So the first one which we have is, so this one's for Ilya, and it asks, doesn't the skip n-gram approach work better for item to vec rather than CB or W?
It depends on an application. So in this demonstration, and actually in some real projects, we use CUB approach, but this is not, it's important to understand that this is not typical NLP application. So here, it's more difficult, it's this learnings from NLP space, these best practices from NLP space, they are not necessarily can be applied to this application in a straightforward way. So typically, it still requires some experimentation and trying different techniques, like different flavors of word-to-vec model in particular.
Perfect. Then we have another question for John. I see John, you already answered it in the text form, but just for everyone's convenience, maybe I'll ask you the same question again. On one of your slides, like no shadow IT on your slide of critical components, can you elaborate on that? Large enterprises have a lot of operational silos. Their operational IT cannot be combined with compute for BI and data science. And that's commonly known as shadow IT. So can you talk more about that?
So for some organizations, they can't combine their operational IT with compute for B&I data sciences, but for some organizations, they can. The reason why we were saying no shadow IT is because basically IT can still manage, for instance, the role-based access control, as well as the users who are able to access DSS or the environments in which DSS is being hosted on, whether that's in the cloud, on-prem, or even on hybrid. You still have the opportunity as an IT organization to say, okay, we're going to give you access to these different data sources based on the role-based access control permissions that each of you have assigned to each other. And that can also come back and say, we can orchestrate where you can manage DSS and build your workflows and run the computation with respect to those workflows when it comes to data preparation or data engineering or building your predictive models inside of cloud environments like AWS and Azure and GCP, because they're able to restrict what users are using DSS and also what permissions those users have. So it kind of depends. The reason why we say no shadow IT is because you don't have to have a user or a department just go into AWS and build their own environment. And then IT is not aware of it. And then when IT finds out, they got to make sure that whatever environments were built are compliant to the business, as well as there's the proper securities in place. With respect to DSS, IT can still take ownership of that at the higher level, not really at the lower level. They don't need to make sure what people are building correctly, just need to make sure that people have certain restrictions to the permissions that they have with respect to projects, and then also restriction what infrastructure is available for each of them to actually use. So that's what I was trying to say when I was trying to respond to that. And please let me know if that answered your question or if I went off a little bit there. Thank you, everybody, and thank you for attending. We appreciate your time, and afterwards you should be able to receive the email with the recordings. And if you have any other questions, please let us know or send us an email. We'll do our best to respond. So when you say, there is a question that just came up. When you say, do you plan on incorporating deep reinforcement learning? So we do enable you to use your libraries with respect to deep reinforcement learning. We don't really have a restriction on that. It just depends on which libraries and which programming language you're trying to do that with. For instance, if you're going to use Python for that or like TensorFlow, then we do enable you to actually use those libraries and also the technologies that would support for you to actually implement deep reinforcement learning. It's not something that we have by default. It's something that we enable you to do. Does that answer your question? I guess so. Okay. Perfect. Thank you.